This video will discuss how to find and define the amplitude, frequency, and period for sine and cosine functions. Given the function f of x is equal to a sine of bx plus c, the absolute value of a represents the amplitude. The amplitude is the vertical distance from the midline to the max or min of the curve. It is the height or the magnitude of the function. Given the function y is equal to sine of x, which we can see here graphed in blue, we can see that the amplitude or the height of the graph is 1. If you look at the second function, y is equal to 0.5 sine of x. The x values, or the 5 key points, will stay the same, but each of our y values will end up changing. The graph is only going to go half as high or half as low. So in this case, our amplitude for the graph y is equal to 1/2 sine of x would be equal to 0.5. And each of our y values would also change as well, like we were multiplying by 0.5. So this would be 0 times 0.5 would be equal to 0. 1 times 0.5 would be 0.5. 0, negative 0.5, and 0. So plotting the new graph in green, we would have the ordered pairs 0, 0, 90, 0.5, 180, 0, 270, negative 0.5, and 360, 0. Applying what we saw in our second function, it's easy to predict what will happen in our third. Each y value or output will change by a factor of 3 as compared to our parent sine of x function. So given y is equal to 3 sine of x, our new output values will be 0, 3, 0, negative 3, and 0. Our a value in this function is 3. The absolute value of 3 is equal to 3. Plotting this point, we can see how our height of our graph now changes. Our points will now be 0, 0, 90, positive 3, 180, 0, 270, negative 3, and 360, 0. We can see how the height of our graph is changing based on our a value. For our final function, y is equal to the negative sine of x, shown in red, we will still have an amplitude that's equal to 1. In this case, our a value is equal to a negative 1. The absolute value of negative 1 is equal to a positive 1. When we graph this, our function will look different though, because the negative will cause a reflection of our parent function over the x-axis. Our new output values will end up being 0, negative 1, 0, 1, and 0. To plot this graph, we can see our starting point of 0, 0, 90, negative 1, 180, 0, 270, positive 1, and 360, 0. When we compare this graph, our red graph, to our original parent function shown in blue, we can see that they are indeed reflections over the x-axis. These rules apply to the cosine functions as well. You can see here how the amplitude of each graphed cosine function is equal to the absolute value of its a value. Next up is frequency and period. Until now, we have only looked at the values of sine x and cosine x functions between 0 and 360 degrees. However, it is possible for trig functions to have values beyond that range. For example, it is possible to take the sine of 720 degrees or the cosine of negative 180. Trig graphs are periodic. That means that a pattern will repeat. I can show an example of a sine function going beyond 360 degrees by repeating our 5 key points. Our 5 key points of sine being output values of 0, 1, 0, negative 1, 0. Repeating my function now, or pattern, goes back to 1, 0, negative 1, 0. Repeating it for a third time, 1, 0, negative 1, 0. So here I can see 3 sine curves graphed. This repeating pattern shows how the function oscillates between the maximum and minimum points. Now we can move on to the period of a trig function. The period is going to be the horizontal length of one cycle, how many degrees it takes to complete one full curve. If I was to take a look over here at my y equals cosine of x function that I've graphed, I can see that in order to complete the cosine function, meaning my 5 key points, I have to go from 0 to 360. Therefore, the period for a basic cosine graph is 360. After that, the function just repeats. My frequency is equal to 1 because from 0 to 360, I am able to complete one full curve. The frequency is the number of curves that are completed from 0 to 360 degrees. From 0 to 360 on this graph, I can see I was able to complete one curve. The frequency will also be equal to the b value of the function. When b equals something other than 1, the graph has a horizontal compression or stretch. Shown in red, I have y equals the sine of 2x. My b value equals 2. Therefore, I know my frequency is 2. Remember, this means that from 0 to 360 degrees, 2 sine curves will be completed. The period is equal to 360 divided by b. In this case, I have 360 divided by 2. Therefore, the period for my function sine of 2x is equal to 180 degrees. In other words, this means that it takes only 180 degrees to complete one cycle. When graphing my function y equals sine of 2x, everything is still based around our 5 key points, shown here in blue. Everything based on the parent function. Except in this case, our x values are going to change. When I'm graphing, I have to change my inputs to accommodate my new period of 180 degrees. My starting point will still be at 0 degrees. However, to find the remaining inputs, I need to divide my period of 180 degrees by the 4 remaining points. That means that each interval will be by 45 degrees. So my 5 points inputs will now be 0, 45 degrees, 90 degrees, 135 degrees, and 180 degrees. Because this graph has just been compressed together, the x values are what's changing, but my y values, or my outputs, will remain the same. 0, 1, 0, -1, and 0. If I was to plot these new points, I should get a complete sine curve from 0 to 180 degrees. So I plot my point 0, 0, then 45, 1, 90, 0, 135 is -1, and 180 is 0. And there we have a sine curve that is compressed to have one complete curve occurring between 0 and 180 degrees instead of 0 and 360 degrees. If I wanted to, I could continue this curve by repeating this pattern of my points of 0, 1, 0, -1, 0 to create a second curve complete a second curve, so it would have two curves graphed between 0 and 360. So 0 up to 1, 0, -1, 0. And now we can see that our period of 2 does indeed match. In the next problem, I can see my basic parent cosine curve graphed in blue. The second function, y is equal to cosine of 1/2 of x, has a b value equal to 1/2. Therefore, the frequency equals 1/2. Remember, what this means is that half of the trig function will be completed from 0 to 360 degrees. The period for my cosine 1/2 x function is still going to be equal to 360 divided by b. In this case, my b value is equal to 1/2. So when I do the substitution of 360 divided by 1/2, that's equal to 720 degrees. Remember what the period means and what the 720 represents. This means that one complete curve will be completed from 0 to 720 degrees. To find my 5 key points, I'm going to take the 720 degrees and divide it by 4. This means that I will have a key point every 180 degrees. From here, I can fill out my table and have my points of my input or x values being 0, 180, 360, 540, and 720 degrees. My output values, my y values, are going to stay the same. 1, 0, -1, 0, and +1. Generally, when we graph, we are only asked to graph from 0 to 360 degrees. But we can extend this graph to 720 so we can see the complete curve. So if I started to plot my points of 0, +1, 180, 0, 360, -1, we can see how the graph is getting stretched out here. So a lot of times we're just graphing to that 360, so I would stop. But if I wanted to extend it out to see my complete curve to show that my b value, my frequency, and period were indeed correct, that it's going to take from 0 to 720 for a complete curve and only get half of a curve to 360, I can continue this process of 540, 0, and 720, positive 1. So when I connect my points, I can see my complete cosine curve that has had a stretch to it. The last term to discuss is midline. This is the c value when given our standard function y is equal to a sine or cosine b of x plus c. The midline is going to be a horizontal center line that is parallel to our x-axis. The function will oscillate above and below the midline, making it the halfway point between our max and min values of our graph. The equation of the midline is going to be y equals c. My input values, meaning my x values of my 5 main points, will not change. However, the outputs will. This time, we will add our c values to our given function. If we go ahead and take a look at our function, y is equal to the cosine of x plus 1, my input values will all remain the same. My output values will differ from my parent function, though, because each point will be shifted up 1. This is going to be a vertical shift. From here, I would have 0 degrees would be equal to 2. 90 degrees is 1. 180 degrees is equal to 0. 270 degrees is equal to 1. And 360 degrees is equal to 2. When I plot these points, I can see the direct relationship between my blue parent function and my green function that has been shifted up 1 unit. Now, if we take a look at my last function here, my yellow graph of y is equal to the cosine of x minus 2, each of these graphs, each of these ordered pairs or points will compare to the original parent function by a vertical shift of down 2. So at 0, I'll have the point negative 1. 0 degrees is equal to negative 2. 180 degrees will be negative 3. 270 is equal to a negative 2. And 360 is equal to a negative 1. If I was to plot these points now, at 0, negative 1, 90, negative 2, 100, negative 3, 270 degrees, negative 2, and 360, negative 1, again, we can see the only change that has happened here between my yellow graph and my blue graph is that there has been a vertical shift. In this case, down 2 units. To recap here, the amplitude is always going to represent the height of the graph and can be found by looking at the a value in our given function. This is also going to represent a vertical stretch or compression. The frequency and period are both related to our green b value of our function. The frequency is how many cycles from 0 to 360 degrees. It will always equal the b value of our function. The period of a given trig function is how long it takes to complete one full cycle. This answer will be in degrees or radians. The period is equal to, in our case, 360 degrees divided by our b value. A change in the b value will represent a horizontal stretch or compression in the graph. And lastly, we have our midline, our c value. This will shift our graph up or down.